In the previous chapter, chapter 10, we investigated two-dimensional figures, polygons, all sorts of different shapes. In this unit, or in this video, we're going to come back to those, and we are going to investigate their area and their perimeter. So the distance around the outside is that perimeter, and the space on the inside is their area. So let's take a look at that. Here is our overview where we'll talk about, first of all, kind of the origin story, right? Like what did we use before we developed standard system of measurements? Then what are our standard units for measuring area, both in the English system and the metric system? We'll talk about calculating perimeter, and then area of specific polygons, including rectangles, parallelograms, triangles, and trapezoids. And then we'll talk about circles. But I do have an opening problem for you to do, and we will come back to this at the end of the last video for this section. And it says this: each of the 10 equilateral triangles in the following figure has side lengths of 1 unit. So this, if I can get my marker to work, so this length is 1 unit. This length is 1 unit, and so on, right? And for this figure, the entire perimeter being the distance around, would be 12, because we had 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1. So the question to you is, the challenger is, what would the perimeter be of this figure if we extended it to include 50 triangles? This one has 10 triangles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we extended that to 50, what would its perimeter be? Okay, so with that, we'll start our conversation about area and non-standard units of area. And what is area? Area is the amount of space it takes to cover a flat surface. This originated in plots of land, right? Property owners needed to measure the space that they owned, or farmers, the space of land that they own, their plots of land. We need to measure panes of glass or floors when we want to carpet it, or walls when we want to paint it. We need to be able to measure area. And the most convenient shape that really is found for measuring area is the square. And so we're going to take a look at a sort of weird looking picture here, a weird looking figure. And the question to you is, if we covered it, hold on, with squares, just going to draw it on here. If we took a square that was this big, so one of these, right? We took one of those. How many of these would it take to cover the figure that's shaded inside? So take a moment and answer that. So when we ask that question, a lot of times young children will misinterpret this question. The correct answer is 4. 4 of those. Well, because one of these covers this one, a second one covers this one, but then we have these halves. So here's a half, here's another half, here's a half, and here's another half. So it don't have to be measuring in full units, right? And so 1, 2, these make a third, these make a fourth. Now, what if we change that? What if we changed it? And instead, let me redraw this. What if we asked, how many of these does it take to cover this figure? Take a moment to do that. Now we're measuring in these triangles. And so we can see we have one here, we have another one here. And even though they're rotated a little bit, and we might have to take these squares and cut them in half. We have another one here, cut this one in half, 2 more, and then 2 more, and see we had 8 total figures of those small triangles that would cover that figure. So these non-standard shapes, right? We can use really anything we want to cover flat space and get some sort of estimate. Historically, we've parceled out land in terms of acres. In the over time, different units of area became a little more standardized. And so let's take a look at what some more standard units of area would be. As I said earlier, we found that the square tends to be the most convenient shape to measure area in. And so imagine we had a ruler and we sketched out a square that measured an inch by an inch on all sides. We say that this thing right here is 1 square inch. We often abbreviate it, as I mentioned in the previous section, 1 inch with a little 2 for the square. Where do we get that? Because when you're finding the area, you multiply 1 inch by 1 inch. 1 times 1 is 1, and inch times inch is inch to the 2nd power. So this thing is 1 square inch. And so if we had some sort of figure and we wanted to know its area, we would take these and just start duplicating those things on this figure and see how many it would take to cover it. That's how you find area. And so we can also use things other than inches. We can measure space depending on the thing that we're trying to cover. We can measure in a square foot, which we would abbreviate 1 square foot like that. We could also measure in a square yard if we wanted to, which is 1 square yard. You can see where I'm going with this. We can measure in a square mile if we're talking about land, perhaps. And we say 1 mile squared. Now those get progressively bigger and bigger. But the idea is we are working with a perfect square here and saying how many of these does it take to cover an entire space. Now, we can go between these types of measurements and say maybe we have a certain number of square feet and we want to know how many square inches that would be. So let's take a look at this diagram right here. So we know from before that 1 foot contains 12 inches. So if we plot out a square like this one that measures 1 foot by 1 foot, you can see that if we break it down into inches, there are 12 on each side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And each one of these units is 1 square inch. So the entire thing is a square foot. Each individual square there is a square inch. So 12 this way by 12 this way is 144. So 144 square inches is equal to 1 square foot. They cover the exact same amount of space. So my next question to you is this, based on what we just talked about. How many square feet equal 1 square yard? Take a moment and see if you can sketch that out. How many square feet equal 1 square yard? Well, hopefully you remember that 1 yard is equal to 3 feet. And so if we look at a square that measures 1 yard on both sides, and we remember that a yard is 3 feet, that means it's broken up into 9 of these squares, each of which is a square foot. So 1 square yard is equal to 9 square feet. Each one of these things is a square foot. It would measure a foot on each side. And so here's a chart that summarizes some of those common units for area in terms of some other unit of area. So again, we already talked about this first couple. A square foot is equal to 144 square inches. A square yard is 9 square feet. An acre is a little bit different of a measurement. It's just common for property. It's actually 43,560 square feet. And then a square mile, you remember how many feet are in a mile from a previous section? 1 mile is equal to 5,280 feet. So if we sketched out a square, let's do a better job with my square. We sketched out a square that measured 1 mile by 1 mile. That would be the same thing as 5,280 feet by 5,280 feet. And multiplying those two numbers together, we get this, 27,878,400 square feet. And we can also do this in the metric system. And so we can measure in square meters. We can measure in square centimeters. We can measure in square millimeters. Now, these are certainly not to scale. You remember from a previous video that a centimeter, if I shrink it to about that size, 100 centimeters fit into a meter. So if we were going to draw this to scale, this side would have to be 100 times as big as this side. Okay, but we can really use any unit of length and square it. So here is a question for you related to the previous topic, but now with the metric system. See if we can figure out these relationships. How many square millimeters are in a square centimeter? And how many square centimeters are there in a square meter? Take a minute to see if you can answer those questions based on what we already know. So let's draw it. If we have a square and we have a square centimeter, that means that there is a centimeter on both sides. Hopefully you remember that a centimeter is the same as 10 millimeters. 10 millimeters. So if we have a square that measures a centimeter on each side, that's the same as 10 millimeters. That means this square could be broken up into 100 square millimeters. So the answer to question 1 is 100 square millimeters. For the second question, how many square centimeters are in a square meter? Well, I told you a moment ago with the previous drawing, if we have a square that measures 1 meter on each side, there are 100 centimeters in a meter. And so if we broke this up into 100 squares vertically and horizontally, and we multiplied 100 times 100, that would be 10,000 square centimeters. 10,000 square centimeters. Here is a chart similar to the last one that relates some of these different metric measurements to each other. We talked about the first one, the last one. A square kilometer would be 1,000 meters by 1,000 meters, which is 1 million square meters. So that at least gets us oriented to the idea of area. Now let's talk about briefly perimeter. So what is perimeter? Perimeter can be thought of as the length of the boundary of some figure. And it can be done to anything with straight sides, right? It doesn't matter what the shape looks like. As long as it has straight sides, we can measure them with the ruler, and we would find out what the length of this side is, and this side, and this side, and this side. And we would just find all those lengths, and we would add them up. So that's what perimeter means. So perimeter, if I can write, perimeter is equal to the sum of all sides. As long as it has at least 3 straight sides, then we can find its perimeter. Now, one of the interesting relationships between perimeter and area is that a lot of people think that if some area has a, let me rephrase this. Most people assume that perimeter and area are related to each other in the fact that if something has a bigger perimeter, it should have a bigger area. This is a classic problem for young students to investigate. It often a common scenario is fencing in an area of land. Maybe you have to put a garden up, and one person uses this much fencing, another person uses this much fencing. Does it mean that the one with more fencing had a bigger area? And that's not necessarily true. And so we're just going to take a quick investigation of a picture. And I have two very simple drawings for you. And my question, or the first thing we're going to observe is that their areas are exactly the same. Areas are the same. Why? Because they are both made up of, we'll say these are square centimeters, each of these squares. They both have 4 centimeters squared. Your job is to find the perimeter of each figure, assuming again that each of these lengths is 1 centimeter. Go ahead and do that. You'll notice on the first figure, our perimeter is 1, 1, 1, 1, 1, 1, 1, 1. So we had 8 of those, right? So the perimeter is 8 centimeters for figure 1. For figure 2, it's here 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. How many of those do we have? 10. Perimeter was equal to 10 centimeters. So these two figures had exactly the same area, but 2 different perimeters. So how about this? Can you look at these 2 pictures and determine the area and the perimeter of them in centimeters, right? They're both measured in centimeters, so the area in square centimeters, the perimeter in centimeters. Go ahead and see if you can answer that question. So they're both sort of related in the fact that this is 1 centimeter tall, and so is this, right? This is also 1 centimeter. This one looks a little bit easier. So we're going to measure this 1 centimeter. This is the same 1 centimeter. So if I'm going to measure the perimeter first, I have 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, because we had 3 across the top. We also have 3 across the bottom. So P is 10 centimeters here. How about number 1? Well, we had 1 here. We've got another one here, so that's 2. We got some of these partial figures. I'm going to come back to those. So again, 1, 2, 3, 4, 5, 6, 7, 8. But then what do we have here? We've got almost like 2 partials that would add up to 1 because they're the same length as from here to here as here to here. So that would be 8.5, 9, and we have the same thing happening here, 9.5, 10. So this also has a perimeter of 10 centimeters. Double check that if you want, right? Go ahead and try that again. Examine these. Make sure that you can see that this length here plus this length here is the same as this length here. If you just sort of trace those, imagine those coming straight over, they're going to make that entire height. But what about the areas of these? Well, again, the first one, if I draw some guidelines there and there, and here, we can see that the area of this is going to be 4 centimeters squared. 1, 2, 3, and 4. For the first one, if I draw my line here and here, Well, this is only 1, 2, 3. The area is 3 centimeters squared. So again, this is sort of a classic problem for students to investigate. Uh, Here we saw two figures that had the same perimeter, but different areas. In the previous problem, we had two figures with the same areas with different perimeters. And a sort of challenging question for a lot of students is how can you sort of maximize your area with a given perimeter and have them investigate all sorts of different scenarios.